The McGinty Equation, or MEQ, is not just a set of symbols on a chalkboard, it represents a pivotal breakthrough in the annals of physics, offering a theoretical framework that integrates quantum mechanics and general relativity. This equation has ignited the scientific community's imagination, suggesting that the eerie phenomena of wormholes might not only be plausible but also observable and stable under quantum corrections. The significance of the MEQ stretches beyond academic curiosity. Its validation could pave the way for advancements in quantum computing, space travel, and even our basic understanding of the universe's fabric. This introductory section sets the stage for a deeper exploration into the specific predictions and experimental setups that could potentially confirm the McGinty equation's bold assertions. Wormholes have long captivated the minds of scientists and science fiction enthusiasts alike, portrayed as gateways to distant realms or shortcuts through space-time. The MEQ posits that with quantum corrections, minute adjustments accounting for quantum mechanics, these fantastical structures could be stabilized, transforming them from theoretical curiosities into potential scientific realities. Understanding quantum corrections involves delving into the quantum foam of space-time, where the fabric of the universe is subject not only to the curves of Einsteinian physics, but also to the probabilistic nature of quantum mechanics. This section examines how these corrections could feasibly lead to stable wormholes, thereby supporting one of MEQ's foundational predictions. Observable quantum effects within wormhole geometries represent a direct pathway to validating the McGinty equation. Such effects could manifest as unique particle interactions or unusual energy distributions, observable with current or near-future technology. This section explores the types of quantum effects that might be detectable in the context of wormholes and discusses the significance of these observations. It also outlines the experimental setups and technologies that could be employed to capture these elusive quantum signatures, marking a crucial step in substantiating the MEQ framework. In the realm of wormhole physics, exotic matter, material with negative energy density, is a theoretical necessity. The MEQ's prediction that specific types of exotic matter can stabilize wormholes hinges on the existence and behavior of these bizarre materials. This part delves into what constitutes exotic matter, the theoretical basis for its interaction with wormholes, and how its presence could be experimentally verified. It also considers the broader implications of discovering such matter, not only for wormhole stability, but for the entire field of quantum physics and material science. If wormholes can be stabilized, the next monumental question is whether they can be traversed or used for information transfer. The MEQ suggests that these tunnels through space-time could indeed allow for such possibilities, potentially revolutionizing communications and even leading to unorthodox modes of transportation. This section explains the concept of wormhole traversability, explores the theoretical mechanics behind it, and discusses potential experimental approaches to test this phenomenon. It also speculates on the practical applications of reliable information transfer via wormholes, particularly in the fields of quantum computing and secure communications. Gravitational waves, ripples in the fabric of space-time, have already been detected, confirming a major prediction of general relativity. The MEQ extends this concept by predicting specific wave signatures resulting from wormhole interactions, which could serve as indirect evidence of their existence. This part outlines the nature of these predicted gravitational wave signatures and how current and future gravitational wave observatories might be tuned to detect them. It highlights the technical challenges and the potential breakthroughs that could come from such observations, reinforcing the MEQ's validity. Quantum gravity remains one of the most elusive concepts in theoretical physics. proposing a framework that integrates the principles of quantum mechanics with gravitational forces. The MEQ addresses this integration, predicting specific impacts of quantum gravity on the geometry of wormholes. This section explains the principles of quantum gravity as they relate to the MEQ and discusses how these theoretical principles could alter our understanding of space-time geometry. It also considers the experimental setups that might one day measure these impacts, potentially confirming or refuting one of the MEQ's core components. Quantum coherence, the property that allows quantum systems to exhibit superposition and entanglement, faces significant challenges in curved space-time. The MEQ predicts that despite these challenges, coherence can be maintained, which would have profound implications for quantum computing and communication technologies. This section explores the concept of quantum coherence, the difficulties it encounters in curved space-time, and how the MEQ's predictions could be experimentally tested. It also discusses the broader implications of maintaining coherence in such extreme conditions, potentially leading to robust quantum computing systems that could operate in space or other high-gravity environments. The intriguing possibility that wormhole fields could modify the properties of standard quantum particles is another revolutionary aspect of the MEQ. If true, this could provide a new understanding of particle physics and force carriers in quantum fields. This part examines how wormhole fields might influence particle properties, what changes could be expected, and how these modifications could be experimentally observed. It also considers the implications of such findings for the standard model of particle physics and beyond. The concept of negative energy is central to the existence and stability of wormholes, according to the MEQ. However, generating and maintaining negative energy in a controlled manner poses significant scientific and technical challenges. This section discusses the theoretical basis for negative energy in wormhole throats, the current understanding of this exotic form of energy, and the experimental approaches that could be used to minimize and measure it. It also explores the potential risks and rewards of manipulating negative energy, a topic of great interest and controversy in modern physics. Quantum teleportation through wormhole interfaces, as predicted by the MEQ, could revolutionize the field of information technology, particularly in secure communications and quantum computing. This form of teleportation would rely on the entanglement of quantum states across space-time, facilitated by the wormhole's unique properties. This part outlines the theoretical framework for quantum teleportation via wormholes, discusses the potential experiments that could demonstrate this phenomenon, and considers the practical applications of such a technology. It also highlights the challenges and potential breakthroughs associated with implementing quantum teleportation on a practical scale. The MEQ postulates that effects from higher dimensional spacetime could significantly influence the behavior of quantum fields. This prediction opens up new avenues for understanding the fabric of the universe and the fundamental forces that govern it. This section delves into the role of extra dimensions in modifying quantum field behavior, how these effects could be experimentally detected, and the theoretical models that support this aspect of the MEQ. It also considers the implications of discovering higher dimensional effects, which could lead to a more comprehensive understanding of universe's structure and its underlying laws. Gravitational redshift, where light or other forms of radiation lose energy while escaping a gravitational field, is a well-documented phenomenon. The MEQ predicts that this effect could vary significantly in the environments around wormholes, providing another potential method for their detection. This part explains gravitational redshift and how it might be measured differently near wormholes. It discusses the theoretical and experimental methods to detect these variations and the significance of such findings in the broader context of general relativity and quantum mechanics. As we conclude our exploration of the McGinty equation and its profound implications, it becomes clear that the journey is just beginning. Each prediction presents unique challenges and opportunities for the scientific community, promising not only to expand our understanding of the universe, but also to revolutionize technologies and philosophies. This final section summarizes the key points discussed throughout the essay and looks forward to the future research directions that could emerge from the validation of the MEQ. It underscores the collaborative effort required across various disciplines of physics and beyond, highlighting the interdisciplinary nature of this monumental scientific endeavor. The McGinty equation stands not merely as a theoretical curiosity, but as a beacon guiding us toward a deeper understanding of the cosmos. Its potential validation holds the promise of unlocking new scientific and technological frontiers, making it one of the most exciting topics in contemporary physics.